All right, now I'm going to come back to section 6 here. This is where we talk about Gibbs free energy. And this is, there's a derivation here. And it was described by somebody named Gibbs. So if we start with the equation here, that delta S of the universe is delta S of the system plus delta S of the surroundings. So if we substitute delta S of the surroundings, as we had figured out in a previous section, negative delta H of the system divided by temperature in Kelvin. All right, so let's substitute that in here. So we know that delta S of the universe equals delta S of the system minus, or you can say plus negative, delta H of the system divided by temperature in Kelvin. All right, so now we don't like things in the denominator, so we want to get rid of this negative here. So we're going to multiply by negative t. So we multiply everything by negative t. You get negative t delta S of the universe equals t delta S of the system plus delta H of the system. So we're going to drop the system subscripts. So negative t delta S of the universe equals t delta S plus delta H. And here, all of our delta H and S values are understood to be the system. So the equation for Gibbs free energy, we're going to use this, just calm down, is G equals H minus TS. G is Gibbs free energy. H is the enthalpy. T equals temperature in Kelvin. And S equals entropy. All right, so Gibbs free energy is a really, really important thermodynamic concept, particularly if you're going into engineering, because it is what represents chemical potential. Chemical potential is analogous to mechanical potential energy. And if you think mechanical potential energy, so a ball sitting on the top of a desk has no kinetic energy, all potential energy. And it's naturally going to move from high potential energy to the lowest potential energy. So just like if you move the ball off the top of the desk, it's going to fall until it has zero potential energy. It stops. So Gibbs free energy represents that same concept for chemicals. So for a reaction, the potential energy of a reaction. Now here, virtually impossible to measure exact quantities. These are all state functions because enthalpy is a state function, entropy is a state function, temperature is just a variable. So these are all state functions, so that means by inference, G is a state function. So we are going to represent the changes of these state functions. All right, so we know that T delta, oh my goodness, T, negative T delta S of the universe, I'm just bringing this from right up here, equals delta H minus T delta S. Oh, I'll multiply by negative T up there. Missed my negative signs. I was like, there's something not right up there. Okay, so then we rearranged. So we rearrange it there. So you can say equals delta H minus T delta S. That tends to be the preferred formula there. All right. And so now here we're going to say negative T delta S of the universe. We're just going to now call that delta G. So we're going to use this Gibbs free energy equation, which is this: delta G equals delta H minus T delta S in order to predict spontaneity. So this is what predicts spontaneity. So we used entropy, but we had to sometimes think about the entropy of the system and surroundings, and that got confusing. Enthalpy we couldn't use to predict. This is what we predict. This is important. You predict spontaneity using delta G. All right, what does this mean? All right, a decrease in Gibbs free energy, meaning delta G is less than 0, delta G is negative, corresponds to a spontaneous process. Think about this, if you think about it in terms of mechanical potential energy, so this represents a ball that's that's on the top of the table. It's going to naturally fall down. So it's going to decrease. So decrease in Gibbs free energy, it's losing potential energy. This is a good thing. All right. An increase in Gibbs free energy, meaning delta G is positive, greater than 0, corresponds to a non-spontaneous process. Okay. So delta G sort of goes along with delta H. So when enthalpy is negative, release of heat tends to be thermodynamically favored. Delta H is positive, thermodynamically unfavored. This is the actual why it happens. Okay, so now there's 4 scenarios that we can deal with. So remember here, delta G equals delta H minus T delta S. So let's look at these factors. First thing, delta H can be negative. So when delta H is negative, and let's look at when delta S is positive. So here, negative and minus T delta S, so that's going to be negative. So delta G is always negative. So that means it is spontaneous. So we're going to say spontaneous at all temperatures. All right. That's the easy one. What happens if delta H is positive and delta S is negative? So here we have a positive. So this would be a positive, and then we have minus a negative, or times a negative. So minus a negative, so that's a positive. So positive plus positive, delta G is always positive, so it would be non-spontaneous at all temperatures. Science tests absolutely love to ask these questions. I know because I've taken a bunch of them. Now, those are the easy ones. Now, let's talk about what happens when delta G and delta S are both negative. Okay, so here you can have, so delta H is negative. That's a good thing. And so when we have minus T delta S. All right, so this negative can dominate as long as the temperature is, as long as this term isn't too big. So this would be the temperature would not be large. So it would be negative or positive. So this is at low temperatures, this is at high temperatures. So when they're both negative, this would be spontaneous. Spontaneous only at low temperatures. Now, before you go, well, what's a low temperature? It depends on the reaction. There's not really a good answer, but so it's spontaneous at low temperatures. You can think about this like the freezing of water. So it's an exothermic process, but there's an increase or a decrease in entropy of the system. So it's only spontaneous at low temperatures. Think about it like that. So in that case, it would be 0 degrees. The other scenario, when delta H is positive and delta S is positive. In this case, delta H is the one that has to be overcome. So delta S is positive, so this term has to be high enough to overcome the positive delta H. So here we need our T to be high. So ultimately it's positive at low temperatures, negative at high temperatures. And yes, the order matters here. So this would be spontaneous at high temperatures. So some memory tricks. I like to look at these just like this. So for these, I kind of plug them in. Now the memory trick here, think about these in terms of temperature. If you have a negative and a negative, this is spontaneous at a negative degree Celsius. It's a memory trick. That's not a rule, but it's just to help you remember. If they're positive and positive, spontaneous at positive temperatures, high temperatures. Again, that's not related to 0. Don't use that as a hard, fast rule, but it helps me conceptually remember what that's going to look like. So let's look here. We're given this reaction. This is a decomposition reaction, and we're given an enthalpy. So here, delta H is, I'm going to put it over here. Delta H is negative. Delta S, we're going from 2 to 3, so entropy is increasing. So if we have negative delta H, positive delta S, delta G is negative, so it's going to be spontaneous at all temperatures. All right, here we go. Freezing of water, liquid to solid. Delta H is negative, so we have a negative delta H. Delta S, we're going from liquid to solid. That is getting more ordered, so less disorder. So that's a negative there. So that means delta G is going to be negative as long as this isn't too big. Positive once that dominates. So it's which component of the equation dominates. If the negative one dominates, it's spontaneous. If the positive one dominates, which would be this one, because you have negative T delta S, then it would be positive. So this means at low temperatures, T delta S is not enough to make delta G positive. So it would be spontaneous. So at low temperatures, spontaneous at low temperatures, think negative temperatures. All right. So here we go. If we have carbon tetrachloride gas going into solid carbon graphite and 2 moles of chlorine gas. Delta H is positive 95.7 kilojoules. Delta S is positive 142.2 joules per Kelvin. So let's calculate delta G at 25 degrees Celsius, determine if it's spontaneous. If it's not spontaneous, determine what temperature it would become spontaneous. Again, these are excellent questions because you can determine a lot of information, a lot of understanding out of one question. So let's do the first part first. Calculate delta G at 25 degrees Celsius. So remember, delta G equals delta H minus T delta S. So delta G, delta H, 95.7. And here we're going to need to be in joules. So times 10 to the third, or times 1,000. I'm just going to say times 1,000 because I don't like scientific notation here. Joules minus temperature at 25 degrees. Well, we don't need 25 degrees. We need plus 273. So that would be 298 Kelvin times delta S, which is 142, good heavens, 142.2 joules per Kelvin. Kelvins go away. All right. So now, 95.7 times 1,000. So 95700 joules minus 298 times 142.2. 42375.6 joules. Remember, units matter here. You have to be careful. Okay, so 95,700 minus that answer. So delta G positive 53,324.4 joules. All right, is the reaction spontaneous? No, delta G is positive. Non-spontaneous. Spontaneous. All right, now, how do we figure out at what temperature it becomes spontaneous? Well, that's going to happen, remember, when delta G is less than 0. So the changing point where that occurs is going to be when delta G equals 0. So we know that when 0 equals delta G, that's going to be, we're going to say the changing point. So now we're going to set up this equation, delta G, delta H minus T delta S. We're going to put in 0 for delta G, and we're going to solve for temperature. Delta H doesn't change. So 95,700 joules minus T times 142.2 joules per Kelvin. All right, so that means negative 95,700 joules equals negative 142.2 joules per Kelvin times T. So now let's divide by negative 142.2 joules per Kelvin. Those will go away. Divided by negative 142.2 joules per Kelvin. Joules go away. Negatives go away. So that means, again, this is simple algebra. You can do this. The math is not hard. All right, so 95,700 divided by 142.2. So, you know, let's just round up here. So temperature, we're going to say 673 kelvins is where it becomes spontaneous. So do we agree that this is a high temperature? Yes, because that corresponds to what, 400 degrees Celsius. That's a high temperature. Cool. All right, lots of information there.